Hi everyone. In this video, we're going to introduce the calculus of logarithmic functions. Let's start with a discussion of the natural logarithm, beginning with its derivative. You've likely seen before that 1 over x is the derivative of ln of x. But why is this true? Let's actually prove it. The proof starts with this function, y equals ln of x, and what we want to do is calculate the derivative of this function, otherwise known as dy over dx. For that purpose, it would be useful if we eliminated the logarithm from our equation, since that's the part that we don't know how to differentiate already. We can eliminate the natural logarithm by applying the natural exponential, since that represents the inverse operation. In other words, let's apply e to both sides. On the left side, we get e to the y, and on the right side, we get e to the ln x. Now a cancellation law can apply on the right side, and so the logarithm is gone from our equation. And because the logarithm is gone, we can now take our derivative, but we must do so implicitly, since the y in our equation is no longer by itself. Implicit differentiation, as you should remember, starts with applying a derivative with respect to x on both sides. Now, the right-hand side is easy. The derivative of x with respect to x is just 1. And on the left side, we know the derivative of e to the y is just e to the y times the derivative of y according to the chain rule. Now, let's not forget that dy over dx is what we're trying to solve for here. And we can do that now by just dividing by e to the y on both sides. We've now successfully found dy over dx, but this formula is expressed in terms of y, and we'd like it to be expressed in terms of x. That's no problem though. For that, just remind yourself of what is the relationship between y and x in the first place. Knowing that y is equal to ln of x, in our derivative formula, anywhere we see a y, we can literally put ln of x instead. This expresses our derivative in terms of x, which is what we wanted. And as a final step, you can apply the cancellation law here to get the formula 1 over x, which completes our proof. You might remember I said once before that everything we know about logarithms is a consequence of something we know about exponentials. And this proof is just another example of that. We've just seen that the derivative formula for the natural logarithm is actually implied by the derivative of the natural exponential. In general, anytime we know the derivative of a function, we can get the derivative of the inverse function following an approach which is very similar to what we've just seen here. So we'll be doing this sort of argument again in the future when we start calculating derivatives of inverse trig functions, for example. So this is just a strategy to keep in mind for the future. As usual, let's build off of this derivative to come up with a few more useful formulas. For starters, as soon as I know how to take the derivative of ln x, then I also know how to take the derivative of ln of u, where u represents something that's not just an x. You can expect this derivative would be 1 over u, but then the chain rule would apply, so we would need to multiply by the derivative of u, whatever that happens to be. Let's try an example. Here we want to find the derivative of ln of the absolute value of x. And you might not see why right at the moment, but this is actually a very important example, so make sure to pay attention to this one. For this problem, we're going to need to know how to take the derivative of an absolute value, so let's address that part first. And I expect you've seen before that the absolute value of x can be thought of as root x squared. That's because the process of squaring a number and then taking the square root always returns a positive number, even if you started with a negative number. If this is an unfamiliar fact to you, I suggest taking some time to review the basics of absolute values. But if you agree that the absolute value can be expressed in this way, then inside our logarithm, we can now put root x squared. But to make it easier to find the derivative, that root I'm going to express as a power of 1/2. To make things even easier, you can now use a property of logarithms to bring this exponent out front. And thankfully, the resulting derivative looks actually a lot less intimidating. You might wonder now if we can also bring down the power of 2, but if you did that, you would end up changing the domain of this function. And I'll leave it to you to think about why that is, but I'm going to choose not to bring down the power of 2 for that reason, and just do the derivative as it is here. Since the half here represents a coefficient, we can also pull it outside the derivative operator. So all we're left with now is the derivative of this logarithm. And we know that the derivative of ln of something is 1 over that something times the derivative of the something according to the chain rule. In this case, the something is x squared, and the derivative of that is 2x, so that's what gets multiplied when we use the chain rule. We're done taking the derivative, but there's a few easy simplifications we can make here, and if we do that, we find that 1 over x is our final answer. So it turns out that not only is 1 over x the derivative of ln x, it's also the derivative of ln of the absolute value of x. And that's actually an important enough fact that I'm going to include it here in our list of formulas. Here's the reason why it's important. If we were to ask now for the integral of 1 over u du, this is really asking for a function whose derivative is 1 over u. We could say that's ln of u if we assume u is a positive number, since logarithms can only accept positive inputs. But according to the example we just did, this formula would still be valid if we put an absolute value here. If we do that, we no longer need to assume that u is positive, and that makes for a better integral formula. You'll be using all of these pretty often in this course, so if you haven't already, I suggest putting these on your formula sheet now. Let's try putting these formulas into practice. With the integral you see here, you can make an observation that's going to be really useful in a lot of examples throughout the entire course. And that is that the numerator looks like the derivative of the denominator. After all, 3x squared really is the derivative of x cubed plus 1. And anytime you notice this pattern, it's a good idea to let u equal the denominator. Let's give it a try. When we go to get du, we find that it's 3x squared dx, and that's an expression that appears in our integral, meaning that entire chunk can just be called du. So we get a pretty nice integral, 1 over u du, as a result. Now we can recognize that as ln of the absolute value of u, and we're done. Just don't forget to express u back in terms of x. What you've seen here is a typical example of a situation that actually comes up very often. Whenever the numerator is the derivative of the denominator, we could express that idea by calling this the integral of f prime over f. And just to reiterate, anytime you see this structure, the correct strategy is always to let u equal the denominator. Here's another example. We notice here the denominator is a linear function, and the derivative of a linear function is a constant. So it's worth asking, is this of the form f prime over f? And the answer is almost. In this case, our denominator is 9 minus 2x, and the derivative of that is negative 2. So this is the integral we wish that we had, but unfortunately, it's not the one we actually have. On the other hand, if we want our numerator to be negative 2, we can make that happen if we multiply by negative 2. And that's valid as long as I also divide by negative 2, since that would cancel out the change that I just made to my function. By doing that, we can successfully express this integral in the form of f prime over f, and for those types of integrals, the same approach will work every single time. Always let u equal the denominator. Whenever we do that, du will take the form of our numerator, so just like before, that entire chunk can be called du, and that leaves us once again with this nice integral of 1 over u du. We know that's just ln absolute value of u plus c, and all that's left to do now is express this in terms of x. Considering I've suggested the same method will work every time when I see f prime over f, we might as well see if we can develop a formula for these types of integrals. If we let u equal the denominator, this is always going to play out exactly the same way. Since du is found by taking the derivative, we could express it as f prime of x dx. So as we've seen, the entire chunk in the numerator can be called du, resulting in a simple integral, which we know evaluates to ln absolute value of u, and after that, just express u in terms of x, and you're done. This formula tells us that literally any time our integral takes the form f prime over f, the result will just be the natural log of the denominator with an absolute value. So anytime we recognize this scenario, we can directly apply this concept and skip the details of the substitution entirely if we want to. I suggest putting this one on your formula sheet as well. Let's consider this integral. The denominator here is a quadratic function, and we know the derivative of a quadratic function is a linear function. So anytime we see linear over quadratic, such as what we see here, it's worth asking whether this is of the form f prime over f. Unfortunately, in this case, it's not exactly. The f prime over f integral would require the numerator to be the derivative of the denominator, which in this case would mean we wanted a numerator of 2x plus 3. And the numerator we've been given is not 2x plus 3. But it might be possible to modify our numerator similarly to how we did in the previous example. And in this case, the trick is to notice that our numerator is actually a multiple of 2x plus 3. So in fact, if we factored out a 2 here, we would have the numerator that we want. And with that 2 being a constant, you might as well pull it all the way in front of the integral. The remaining integral here really is of the form f prime over f, and we know the result of that will always be the ln of the denominator. Just don't forget the absolute value as well. This last step could be fully justified by letting u equal the denominator and going through all the steps of that substitution, but with recognition that the substitution plays out exactly the same way every single time, it's fine with me if you just point out the f prime over f form and jump straight to the answer like I did here from this point forward. It's fine with me if you do that. If you prefer though, you can go through the details of the substitution as well, and that's perfectly fine. Something you may have noticed about this example is that it's a linear over an irreducible quadratic. So this was actually a partial fraction. And you should remember that anti-differentiation of partial fractions is an important goal for us, since it would solve the entire problem of anti-differentiating rational functions in general. We've just found that this strategy of letting u equal the denominator can be used for anti-differentiating at least some partial fractions of the linear over irreducible quadratic type. So this at least puts a dent in that goal of anti-differentiating partial fractions. But unfortunately, this strategy only works if the numerator happens to be the derivative of that quadratic, and it's not always possible to force that structure like it was in the example we just did. So we still don't have all the tools to handle those types of situations where the linear function is not the derivative of the quadratic. For that, we would need to study inverse trig functions, so we'll be doing that at some point in the near future. But for now, this is all I have for you, so I'll see you next time.